In this video, we'll be looking at low dropout or LDO regulators. LDO regulators are used to convert a higher input voltage source to a lower output voltage that can supply a load. Very simply speaking, LDOs and linear regulators achieve this voltage drop by dissipating some power as heat. In particular, we'll examine the basic function and how they work, then seeing when we might use them and when we shouldn't use them. When choosing an LDO, it's also important to look out for various parameters, so I'll give you some tips of how to select them and what to watch out for. And finally, we'll look at some layout and routing examples on real-world examples. Here are some PCBs made and assembled by PCBWay that all incorporate LDO regulators, and there can be many reasons for using LDO regulators. What you might notice for 3 out of these 4 PCBs is that these are audio-based, fairly low-noise PCBs. On the left-hand side, we have a USB headphone amplifier with an analog front end that needs to be driven by a low-noise voltage source. Similarly, for the top middle picture, this blue PCB is a digital guitar effects processor, which again has an analog front end. And on the right-hand side, we have a very small USB RF dongle using an ESP32. What at least the PCBs on the left-hand side have in common is that they have low noise requirements, especially for the power section for the analog front ends. We could of course use switching regulators for their efficiency, but these will have rather high harmonic content, which could bleed over audibly into our audio path. This might be one reason you'd want to incorporate LDO regulators into your design. This is for low noise requirements. On the right-hand side, looking in the top right corner, this is the LDL regulator with its surrounding circuitry. The reason I chose it for this design is because of its small size that has to fit on this board, its low noise, and the low amount of external required circuitry. This is in direct contrast to most switching converters, for example step-down or buck converters, which require a lot of additional circuitry. Thank you very much to Altium for sponsoring this video. The PCBs you saw at the beginning of this video were all designed using Altium Designer. And if you'd like to give Altium Designer a try for yourself and check out all the cool new Altium 365 features such as online viewers, version control, MCAD co-designer, please make sure to check out the link in the description below or go to altium.com/YT/PhilsLab and you can get yourself an Altium Designer free trial as well as 25% off your first license purchase. To help you get started with Altium Designer, I have various videos on my channel which gives an STM32 PCB design a complete walkthrough. So an almost 3-hour-long video from project creation to getting your boards ordered with assembly. A big thank you also to PCBWay for sponsoring this video. The PCBs you saw at the beginning of this video were all manufactured and assembled by PCBWay and worked flawlessly when I got them. I'd highly recommend their services and I'll leave a link to them in the description below as well. Make sure also to follow them on Instagram if you want to stay up to date with some cool new PCBs. Also feel free to follow me on Instagram at PhilsLabYT where I post little snippets of PCBs that will be in upcoming videos. Simplicity, size, and noise performance are usually the main determining factors for using LDO regulators in your own hardware designs. For example, this is the backside of one of my audio processing DSP boards. On the bottom right-hand side, we see 2 different regulators. The one on the top right is about a 0.5 amp max capable linear regulator or LDO regulator that supplies an analog section, and on the bottom right we have a beefier 1 amp max capacity LDO regulator for the digital section. So even if I'm feeding digital and analog, I can separate them out into 2 separate supplies and means I can eliminate switching supplies, for example, from this PCB. But there are of course caveats to that, as we'll see, specifically with power wasted and thermal issues. What you might also notice is that these parts are very, very small, even given that they can handle up to about 0.5 amp and 1 amp within certain conditions. A switching regulator will require far more parts, inductors, large output capacitors, maybe even the MOSFETs and diodes themselves, whereas these LDO regulators simply, and a lot of the times, require input-output caps and maybe some feedback or filtering circuitry. Before we go into more detail of what parameters to look out for with a linear regulator, let's look at the function of one of these devices. Here I've drawn up a sketch of the internals and typical external circuitry for a very, very basic linear regulator. Keep in mind, this is just an illustration. The linear regulator itself is contained in this light grey box and needs certain external components. The regulator, of course, is used to take a higher input voltage and convert that, so to speak, to a lower input voltage. This could be, for example, from a 9-volt source to maybe a 3.3-volt load, such as a microcontroller, and so on. Linear regulators come with many input and output voltage variants, output current variants, and more, which we'll see later on. Our input voltage source is connected to the power in and ground terminals of our linear regulator, for which we also need an input capacitor Cin, which provides local energy storage and filtering, and this needs to be placed very close to the regulator, as we'll see in the layout and routing section. On the output side of this linear regulator, we also have an output capacitor for similar reasons, for filtering, bulk decoupling, and energy storage. From that point, after this output capacitor, we can then connect a load or loads. Internally then to the device, and the way we then convert, for example, our input voltage Vin to a lower output voltage Vout is via this contraption in the center within this light gray box. The very basic explanation is that we have a series pass element, which is typically a transistor. This might be a Darlington pair, it might be NPN, PNPs, or FETs, and we need according driving circuitry. And with that pass element, we are utilizing the properties of variable, essentially resistance of our pass element to alter how much heat and power we waste within that pass element, and thus we drop our output voltage by wasting power as heat. And that's as simple as it is. You can think of this pass element very crudely as a variable resistor. The question is then, how do we adjust this variable resistor, so to speak? How do we adjust this variable on resistance of our pass element? And this is using a closed loop feedback circuit comprised of an operational amplifier, a voltage reference, and some sort of feedback path. An operational amplifier, very simply, compares two voltages and produces an output. In this case, we have a reference voltage, which is generated by a precise reference internal to the package. This might be 0.7 or 0.8 or an arbitrary voltage. And this is compared to a feedback voltage, VFB. The feedback voltage is generated either internally or externally to the part, to the linear regulator, by dividing down our output voltage, sensed at the output after the pass element, dividing it down via our resistor divider R1 and R2, and taking the center tap and feeding that back to our op-amp. By comparing Vref, our reference voltage, which is typically a very stable voltage, regardless of input voltage and hopefully regardless of temperature, but of course there are limitations, we compare that reference voltage to our feedback voltage, and then the op-amp changes the output voltage appropriately. This element then needs to be able to drive a suitable series element, a pass element, so for a FET, generate the appropriate voltages that can actually drive the gate, and depending on the applied voltage at the gate or the base of one of these transistors, this will change the on resistance, or how much current we let through, how much power we waste within this part, then changes our output voltage. As our output voltage goes up, our feedback voltage goes up, our Vref is the same, and therefore the output of our op-amp goes low, and this reduces the output voltage, and similarly in the opposite direction. So this is the power of negative feedback. Keep in mind, this is a very, very simple explanation, and this drawing here is a very, very boiled down version of what is actually inside a linear regulator. There are also specific changes that need to be made to make this into an LDO or load dropout regulator, which brings us into the point, what is actually even load dropout? For a typical linear regulator, for example, pin 1 being our input pin and pin 4 being our output voltage pin, we need our input voltage to be a couple of volts, maybe higher than our output voltage. And in certain situations, this can be a problem. The load dropout regulator, or LDO regulator for short, fixes that by adjusting our pass element in a clever way that our input-output differential can be lower, maybe even 200, 300, or a couple hundred millivolts. Therefore, if we need, for example, a 3.3 output voltage, our input voltage could be, for example, 3.6 at a minimum. I've drawn in this variable feedback resistor divider network externally, but oftentimes we can get fixed output voltage LDO regulators, as we'll see. What's important for us then, as we saw that this series or pass element dissipates power as heat to generate a lower output voltage. And this is one of the main limitations of using LDO or linear regulators. We need to somehow dissipate that heat. We need to somehow be able to handle that heat that's generated. And this in comparison to, for example, switching regulators, these are far, far less efficient. What we also then need to pay attention to is how different our input voltage is to our output voltage. If we have a large input-output differential, so to speak, so difference between V in and V out, and a large current draw at the output, this will cause a larger power loss and therefore worse thermals for a particular device. Other things we have to pay attention to are, for example, the package size, which also plays a role with thermals, and what the input and output capacitors need to be. It's very simple to calculate the power that is dissipated in a linear or LDO regulator. We simply need to know the input voltage, the output voltage, and the output current. Let's say we are running from a 9 volt supply as our input, so we'll type in 9 for our input voltage, and our output voltage we want to run, for example, a fairly beefy microcontroller that runs typically at 3.3 volts. If this microcontroller is not doing very much, we could estimate it's in the tens of milliamps and maybe even 100 milliamps at a stretch. We can click on Calculate, and that gives us the power dissipated within the voltage regulator, again due to this series pass element in watts. And even for only 100 milliamps at 3.3 volts, this voltage regulator, this linear one, is generating about 0.6 watts of heat, which is quite significant. We need to find ways of managing to get that away from this part. If we double our output current, you might have guessed already because this is a linear regulator, we double the watts that are dissipated. The power dissipated is directly proportional to the output current. What's also very important, which we spoke about earlier, is our input-output differential. If our input voltage is very large compared to our output voltage, we dissipate more power as well. So if I increase that, for example, to 15 volts and still keep my output current and output voltage the same, I get an even larger power dissipated. The power dissipated in a linear regulator, regardless of LDO or not, is the input voltage minus the output voltage times the output current. And this is something we really have to pay attention to. Looking at a very typical LDO regulator, this is one part I use quite a lot. It's by Max Linear called the SPX3819. And let's briefly browse through the datasheet because that'll give us an indication of what this device is capable of and what also the thermal limits might be. And from that we can derive what the maximum currents for a given input and output voltage this device can sustain. LDO regulators come in very, very many different packages with different pins, maybe enable pins, soft start pins, noise filtering pins, and so on, and that really depends on your specific application. The choice of package, however, is also important for thermals, as we'll see in just a bit. When choosing a linear regulator or LDO regulator, a couple parameters are important. First of all, the nominal allowed maximum output current for the device, and that should be oversized depending on your situation. So if I have a 200 milliamp load, I would choose at least maybe a 300 or 400 milliamp LDO regulator. Important parameters might then also be what type of output voltage noise there is. And that is dependent on your system. If you're powering an MCU, you probably don't need a very low output noise. But if you're powering an analog front end for an audio path, then of course you might need a lower noise. The dropout voltage, as we spoke before, is what the minimum input-output differential can be. In this case, it's 300 millivolts at full load, and it depends on the loading. But for this regulator, let's say at full load, if I have a 3.3 volt output, I need at least about a 3.7 volt input to have this device turn fully on. LDO regulators are available in fixed and adjustable output voltage versions. Typically, these are these nominal increments, 1.2 volts, 3.3, and of course higher ones as well, such as 9, 12, 15, 18 volts, and so forth. For full flexibility, there are pretty much always adjustable output voltage variants of that particular regulator. Then, as we saw in the diagram, we need to attach these external resistors, and depending on the resistor ratio, we can then set various output voltages. In any case, scrolling down, looking at the typical application diagram, you can see how easy to use these parts are. They haven't drawn in the input capacitor here, but we do typically need one. But we have an input voltage, input-output capacitors, ground connection, and that's usually it. This particular device might have an enable signal, where we can turn on and off the device with a logic level signal. In some versions of this device, they also have a bypass pin where we can attach an optional capacitor, maybe 10 or 100 nanofarads, that further reduces the output voltage noise. Another important part of an LDO regulator's datasheet are the operating ratings. We want to stay within the operating ratings and try to stay away from these absolute maximum ratings. For this part, and what's important for LDO regulator choices in general, is the maximum input voltage range. Again, we still have to consider the input-output voltage differential, our LDO dropout rating. So for a 3.3 volt output regulator, we of course can't be at 2.5 volts input. We need to be about 3.7 volts input. Remember also to stay away from very large input-output voltage differentials, as that increases our power dissipation. For thermal properties, which is very interesting, we can calculate the approximate package temperature using these thermal resistances. And this is why I said earlier that package choice is also important. If we choose, for example, a SOT235 package or DFN8 package, they have vastly different thermal resistances. So per watt of power dissipated, the SOT235 package heats up by 191 degrees, and per watt of power dissipated, in comparison, the same part, except a different package, this time a DFN8, only heats up by 59 degrees per watt. If we look at the actual package drawings, we can see why. This SOT23 part, which has a much higher thermal resistance, so it heats up quicker for a given wattage than the counterpart, which you'll see in a second, is that it doesn't have very much mass. The pads are very small, the package is very small, so there's no way really to dissipate that heat. Compare that to the DFN version, which had a significantly lower thermal resistance. This has an exposed pad in the middle where we can use thermal vias and copper pores, ground planes below the part to wick away that heat, so to speak. And that's why this also has a lower thermal resistance, because the package has more area to dissipate that. What's very important also with LDO regulators, and it's a fairly easy choice to make, is the choice of input and output capacitors. Typically, any sensible datasheet will give you recommended values and minimums for these capacitances. Modern LDO regulators will allow you to use very small, multi-layer ceramic capacitors. If you choose wrong capacitors, and if you choose the wrong types of capacitors for many older devices, and even some modern ones, the regulator can become unstable and your output voltage will fluctuate. Typically, the manufacturer will recommend a minimum value, type, and maybe an alternative value and an alternative type. The reason for oftentimes using electrolytic or tantalum is because these specific types of capacitors typically have a higher ESR, which in the case of LDO regulators aids their stability. On the note of choosing the right capacitor, what you also need to pay attention to, especially for ceramic capacitors, and especially for class 2 ceramic capacitors such as X5R, X7R and so on, is the DC bias derating. Typically, capacitors, for example, the one I chose here from Murata, this very lengthy name, is nominally a 1 microfarad capacitor, 16 volt maximum rating, a given temperature range, given dielectric, and a package size of 0603 imperial. If I pull up the graph of DC bias characteristics, meaning on the x-axis we have the applied DC voltage to that capacitor, and on the y-axis we have the capacitance of that capacitor, we see the actual about 1 microfarads of capacitance is only pretty much guaranteed from 0 to about 3 volts. After that, so for example, if we're using our capacitor for a low dropout regulator at the input, maybe at 10 volts, if we look at the graph at 10 volts, the capacitance has dropped significantly to about 40% of its original value, so about 0.4 microfarads. This can impact your stability, this could impact your decoupling effectiveness, and so on, and is a general guideline in any case if you're choosing class 2 ceramic capacitors. An idea to combat the high input-output differential problem is often to use, for example, a switching regulator first if we have a very high input voltage source. In this case, here's an example I found on the internet, up to a 25 volt input, and for example, we need a 3.3 volt output. That's a huge, over 20 volt input-output differential. Even at 0.1 amps or 100 milliamps, we're getting over 2 watts of power dissipated in the LDO, which is simply not feasible in most cases. Therefore, in this example, they've used a buck converter, stepping down from 12 to 24 volts to a far more manageable output voltage, 5 volts, which is still higher than this LDO's dropout voltage, and then using that to generate 3.3 volts, and therefore reducing the power dissipated in the LDO. The buck converter itself is of course a lot more efficient, oftentimes over 90%, and therefore this high input-output voltage differential for this buck converter is no problem, even at higher currents typically. Keep in mind though that using buck converters in your design, as this is a switching converter with magnetic elements, these will typically be more susceptible to EMI problems than, for example, a design that just uses LDOs. Of course, this is a very big generalization as it depends on other circuitry as well, but keep that in mind when comparing buck and LDO converters. A design we saw earlier, which I showed you a picture of after it had been assembled and manufactured, is this DSP guitar pedal I designed a little while back. Due to noise requirements, and because I don't actually have a very high input-output voltage differential, I went with LDO regulators. Also for simplicity, and of course noise requirements due to this being a mixed signal system. I have one of the LDOs at the top here with a certain package, and this feeds the digital section, and far away on the left-hand side I have this smaller LDO which then feeds my analog section. This particular regulator is a Texas Instruments TLV 76733. It's up to 1 amp nominal output current at 3.3 volts. You can see there's hardly any external parts surrounding this, an input and an output capacitor, and it has an internal voltage and generates 3.3 volts at the output without any feedback network. I chose this particular package, again because it has a large exposed thermal pad underneath, to which I can attach vias directly down into internal ground planes and feed away that heat. On the other hand, for this smaller regulator that feeds the analog section, this analog section has very low power and very low current requirements, so I didn't have to really worry about the thermal properties of this device. Again, very simple, an input and an output cap, and that's about it. Let me show you how to lay out and route one of these very simply. Let's go through a brief walkthrough of how to then very simply lay out these very easy to route and lay out LDO regulators. The schematic here for the digital LDO we just saw, we have part U100, we have an input capacitor C102 and an output capacitor C103, both at 2.2 microfarads, and these are 0603 parts. All we have to do is then connect our input voltage at pin 8, output voltage at pin 1, these various ground connections, including our thermally exposed copper pad at the bottom. We have an enable signal, which in this design I've just tied high, so as soon as power is applied, our LDO turns on. You can see we also have a sense trace, and this can be used, for example, with a feedback network, some resistor dividers, to alter the output voltage. For this specific part, this is a fixed 3.3 volt part. This sense trace is only used as a very short feedback trace to sense the output voltage, 3.3 volts, without any dividers. Let's move over to the PCB now. As you can imagine, there's actually not too much to this. We have a regulator, U100, our input capacitor, and our output capacitor. As with switching regulators, but less critically so, we want to keep our loop areas small. Loop areas mean, for example, our loop from pin 8, which is our input power, and the ground connections, and loop will mean our output power connection, so pin 1, and again, our power connections. So pins 8 and 1 are critical, pin 8 being our input, so I have my input capacitor, and therefore I can either place my input capacitor like so, not like so, because this is very, very minimal space. Assembling this, of course, won't work, so we need to move this a fair distance apart, but still close enough to the device. In this case, this is less than a millimeter, and we have nice straightforward connections from pad 8 to our capacitor and pad 6 to our capacitor. Alternatively, because this has an exposed pad in the center, which is also grounded, we could place our bypass capacitor like so, maybe moving it slightly further away, something like this, for example, very crudely done. This might be a less ideal situation, so I prefer a connection, for example, something like this. Remember, on the output side, we have pad 1 or pin 1, and we take our output capacitor and make sure our loops are small, for example, pin 1 to pad of our capacitor and pin 4 to pad of this capacitor. Alternatively, depending on what loop might be better, and because we have this exposed pad, we could place the capacitor something like so. Again, short connections then and short loops. Let's then say we've placed our capacitances like so, symmetrically. Then what we do is take a wide as possible trace from our pads to our pads. So in this case, about 0.35 millimeters is as wide as the pad. We can root out and then, for example, increase our pad width incrementally like so. We want wide, short pads to reduce the inductance of our connections. We can then take this trace, copy it, paste it, and flip it, and then we have the same connection, for example, to our VCC, our power input. Our sense trace is actually pin 3, and that just needs to be a thin trace because that is not carrying any current, it's only sniffing the voltage. And of course, you could feed this sense trace maybe further out to closer to a load to compensate for voltage drops, but we'll just use a thin trace and route it up, for example, like so. Remember, this pad is only to sense the voltage. Our ground connections, because we have internal ground planes on layers 2 and layer 3 of this 4-layer board, place a via and place one via per pad, for example, like so. And then we have a short, for example, wide traces routing into these pads. It depends on your power planes, if you're routing power or not, and how closely spaced your planes are, but sometimes it can also be beneficial to place, for example, our traces and vias like so, if we have internal power planes, and have our vias closer together, again, to minimize inductances. For routed power, typically the guideline is, if you have vias or you're routing with traces, is to space your vias and your traces further apart, because this effectively adds inductance to this connection, to the capacitor, and improves the decoupling for this capacitor and this system then to the rest of the network. Also, again, keeping in mind loop areas, placing the ground via closer to the center of the LDO might be a good choice as well. But given that this is a very non-critical system, connections like this are absolutely fine. And then, for example, here, again, we can route out very crudely like so. Again, we could do the same thing with increasing our track widths. Because my input power is actually coming from the left-hand side, I will then rotate this, and I can simply route in with a wide trace into my capacitor first, and then my LDO. Same thing on the output, I take my output from the capacitor and not directly from the LDO pin, for example like so, and then I route on to my various parts. We are still missing this exposed pad in the center, and we will need to place thermal vias in there, again, to wick away the heat that's being lost due to our series element of our LDO regulator. The vias I placed earlier were 0.7mm pad and 0.3mm drill. If I place those vias, for example, directly like so, we'll get problems with assembly because we'll have paste applied to this pad and these vias can then wick them away. We need to have the vias directly in the pad though, and directly down from the package, because this gives us the maximum benefit of using thermal vias. I could place thermal vias, for example, like here and like here, and then have wide traces going in, but that increases the thermal resistance of my connections. A compromise then is, and we need to do this without adding too much cost to our PCB, is by reducing the hole size. So typically I would go, for example, for 0.25mm drill, maybe a slightly smaller pad, and then place that closer to the outsides and place them, for example, like so. Of course, I can place more vias, but that will increase the chance of solder being wicked away. So I try to avoid placing them directly in the center, maybe more of the outskirts. What we also could do is maybe adjust our solder mask layer, so actually only part of the thermal pad is exposed, but then again, that might also hinder the thermal properties a tiny bit. Again, it's a bit of a compromise. And it's also good to ask your manufacturer what they prefer and if they'll have any assembly problems with having these vias in this pad, and if there's any cost adder. We also have pin 5 lastly, and that's simply the enable signal, and that just needs to be a thin I/O level trace, so maybe a 0.2-0.3mm trace, routed something like so. And that's all there is to routing out and laying out an LDO regulator. Thank you very much for watching this video, and I hope it showed you when and when not to incorporate LDO regulators into your own design. If you do use them, I hope this video showed you how easy it is to incorporate them into your design and what aspects to pay attention to, how to choose external components, and how to then lay out and route your LDO regulator on your design. Make sure to subscribe to the channel to not miss any future videos on hardware design, PCBs, DSP, and embedded firmware. Thanks again for watching. Bye bye.